Good afternoon, everybody. This talk is going to be in two parts. The first part will be about Digby Worthy, or William Digby Worthy, his full name, and it will be about his life up to the time when he started work on the Marconi TAC. And the second section will be on the Marconi TAC itself, covering both where it was used and what it was designed for, and some of the technical information about it as well, how it's configured internally, and a little bit of information on programming it, and an example of a program that I've written in machine code to run on it. Okay, this is William Digby Worthy. Oh, by the way, I'm hoping that Digby's son Peter is on the call at the moment. Yes, he is. Sorry, I can actually see him. William Digby Worthy, born on the 29th of March 1923 in Hartlepool, County Durham, to John William, a teacher, and Ethel May near Johnson. And the first 8 years of his life were happy and uneventful by all accounts. And here's a picture of him. Obviously some very British ceremonial day with his Union Jack. I'm guessing that was about maybe 1930 or a little bit before that. But aged 8, Digby contracted meningitis, and this caused him some problems for the rest of his life. Although there has been some discussion within the family that it may not have been just a problem, it may have actually been an enhancement in some ways, in that it caused him to go in particular directions during his life, which were advantageous to him later on. But the meningitis damaged his memory, and later resulted, round about the age of 13, if I remember rightly, in him suffering from epilepsy. But he was a very bright child and was sensible enough to concentrate on school subjects which didn't require memory so much, such as mathematics and physics, that he could use his logical abilities to get around his memory problems. In fact, he was bright enough to jump a year in primary school, passing his scholarship examination at the age of 10. However, the school of his choice, Pocklington School in Yorkshire, wouldn't accept him early, so he stayed on for another year at primary school and moved there at age 11. This is the current website, or the front screen for the current website of Pocklington School, still going strong. I don't know whether it always did have, but it seems to have a prep school there as well now, so it's got both primary and secondary schools. Still very much working on the same ideas as made it very attractive to Digby when he went there back in the 1930s. At Pocklington School, Digby flourished, and as I said earlier, he worked around his memory problems by using his logical and analytical aptitudes. Now, at 13, he suffered his first epileptic seizure, and about a year later it happened again, and he was prescribed phenobarbital. This was obviously quite effective, and it reduced his seizures to around every 45 days. And as they were mainly during the night, he was usually fine during the day and excelled at school. And not just in his academic subjects, he was also a very good swimmer. He was school swimming captain at one time, and at one year was Victor Ludorum of the school swimming gala. Now this is where we start seeing how unusual he was. He had a great mathematical brain, and at the age of 14, he proved that all the 5 regular solids, that's tetrahedron, cube, octahedron, icosahedron, and duodecahedron, could each be folded from a single sheet of paper, like this. So that's showing how his mathematical abilities connected very well with practical abilities, which isn't necessarily always the case with mathematicians. So he was a good applied mathematician, even at the age of 14. Then at the age of 15, he managed to beg or borrow Meccano construction kit, because it's quite difficult to get hold of at the time. This was wartime, or it was just starting to be wartime, coming up to the war. And he built a differential analyzer out of Meccano construction kit. And this was considered so cutting edge that the English Electric Company displayed it in their Nelson Development Laboratories in Stafford. And here's a photograph of it. Now this photograph, actually, with the text underneath, is taken from a magazine article that was produced some years ago about Meccano, about differential analyzers and integrators made from Meccano kits. One of the things that Digby did that made this much cheaper to make, or you can make it with many fewer parts, was that he used drive belts and pulleys for the linkage between the sections instead of meshed gears. So simplifying it no end. Actually, one thing that's been pointed out is this doesn't seem to be complete. There doesn't seem to be anything at the end here for the to connect up to. So I don't know whether it was ever completed, or if by the time this was photographed, there were some modifications taking place or something. I don't know. Oh, by the way, as you've probably already seen, quite a lot of these photographs are courtesy of Peter Worthy. He holds the copyright for many of them. And if I've missed any, my apologies. Just assume that if I haven't put anything on them, that they're Peter Worthy's photographs. Okay, aged 18, he took his high school certificate and gained distinctions in all 5 subjects and a place at St John's College, Cambridge, with a state scholarship. Now he got a 3-year, actually I think he got a 4-year, extendable to 4-year scholarship. But due to the war, all the degree courses were compressed into 2 years. And Digby gained a first-class honours in engineering sciences, aged 20. And another thing that shows his practical brain was that while he was at Cambridge, he discovered that if you put a bit of condensed milk in the inner tube of your bicycle tires, it made them self-healing in the case of puncture. Now, I'm assuming this is the nestled milk kind of condensed milk, the stuff with lots of sugar in it that's very viscous, rather than the other kind that would just run out, right? As this was wartime, the next step in Digby's career was decided by the Central Register for Scientific and Technical Personnel, and he was allocated a post at Oxford University teaching mechanics and hydraulics. And we don't really have a lot more detail about this, but he, apart from the fact he was there for 3 years, and while he was there, he wrote a paper on magnetic fields in electrical machines, or co-wrote it with Dr. Motz. He then decided that he would go and get himself a mathematics degree. If you remember, the one he got before was an engineering degree. So he went back to Cambridge, but to Balliol College this time, and he had 2 years left of his scholarship. So he did the 3-year mathematics in 2 years and managed to get a 3rd-class degree. Right, and he's here in this picture. You can see where my cursor's pointing. So that's 1945 with his friends at Balliol College. He was asked to join English Electric Research Laboratories at Stafford. If you remember, they're the people who put his Meccano differential analyzer on display. So I guess they may have even approached him directly. If not, I'm sure they would have remembered him if he applied to them. So this is now 1948. And he worked on a number of projects, electrical generation projects mainly, including a control system for the Snowy Mountain Falls Extension hydroelectric power station in Australia. And this is actually a photograph that was in the Times Science Review in 1952, and it's a photograph. And here's Digby standing, and this is it's a power station control system, a network power system, I suppose you might call it. Then this is where he moves on to doing to getting involved in digital computers. So he was seconded to the National Physical Laboratory to work on the Pilot ACE. Now you've probably heard of this. This was a project that was proof of concept design, rather, that was developed by Alan Turing, but he left MPL before the project was completed. So Digby went there. I think certainly by the time Digby got there, the Pilot ACE was working, but he obviously the documentation that hadn't all been done, and they hadn't started really finding useful applications for it. So that was what Digby did. He wrote a programming manual for it, and he wrote some programs for transformer design and airframe analysis. Again, we're getting back to this same thing of he was very much an applied mathematician, so he could use his mathematics, but he could also visualize ways in which that could be useful in the real world. The Pilot ACE was shut down in May 1955 and was given to the Science Museum in London, where it remains today. This photograph shows it on display. I don't think it's still on display. I think it's probably in storage like a lot of the other computers. But that's, you can see it's in a glass case, the sort of traditional way that things are displayed in museums. Not, I must say, the way that we tend to display our computers in our museum. We like to have them working, doing things. Next, Digby's mother persuaded him to apply for the Goodwin Fellowship. Now, this is an award or a bursary or whatever you want to call it, that pays for people to do research. This is people that have been students at St. John's or Christ's College, Cambridge. And of course, St. John's was where he did his engineering degree. And he applied for this award to fund a year in the USA studying computer design and application. And this is the front page of his report that he wrote when he returned. He was there from middle 1942 to 1952 rather to the middle of 1953. And as you can see here, he says, purpose of visit to USA, study of the application of the automatic computing equipment to the solution of scientific and engineering problems and the developments made in equipment for this and the allied field of automatic control systems. And this was his itinerary. And there's a lot of stories about his trip. If you read that report, about because he was really confused when he got to the States, because both his not just his university courses that he did, but when he was a lecturer at university, all of them he lived in. He lived in the accommodation that was provided within the university. When he got to these places in the States, he was completely dumbfounded that they didn't have any accommodation. He had to find his own. And some of it was really pretty dire. He tells a story of falling asleep in one place that had a hole in the window, and he woke up with snow in his bed. Not a very pleasant place to live. I think he found some better ones later on. He was at UCLA, the Institute for Numerical Analysis, and saw the Southwestern Automatic Computer. He was at Stanford and Berkeley, and Berkeley had a simple computer built by students. He was at MIT Computing Laboratory and saw the whirlwind. He was at Harvard Computing Laboratory and saw two computing machines there. He was on the 1st of May 1953, he was back at MIT and he did some studying there on circuit design. And I had a look at their differential analyzer and their power network analyzer and their flight simulator, all which I'm pretty sure were actually mechanical. I mean, they had more in common with his differential analyzer made of Meccano than they did with a digital computer. And then he decided to visit some commercial companies. So he visited IBM New York, Bell Labs at Merry Hill, and while he was there, he met three luminaries of the time. No doubt you recognize at least some of those names. He went to RCA Princeton. He went to the Institute for Advanced Study at Princeton University, Remington Rand at Philadelphia, and they demonstrated the UNIVAC machine to him, Burroughs at Philadelphia. And then from the 3rd of June to the 17th of July, he went to Westinghouse, Pittsburgh, and then he had a holiday in Canada. But his idea of a holiday was to visit lots of companies up there as well. So he visited the Franti factory in Toronto, and he visited Washington, DC. But unfortunately, then he had to cut short his trips because he was called home as his father was dying. Meanwhile, the English Electric Company had decided to build a larger and more practical computer based on the Pilot ACE called the DEUCE, Digital Electronic Universal Computing Engine. So Digby returned to Stafford to help complete work on this. And there we have. Fortunately, neither of those people is Digby, but that's the machine, the only picture of the machine really I could find, the whole machine. Now this is where Digby was transferred to Marconi in Great Baddow near Chelmsford, Essex, to introduce them to the use of computers for control and radar signal processing. And the first project was an early warning system for the Swedish military, codenamed Hat. Now, there is a story about this, how this codename came about, and it seems the first team of engineers that went over to Sweden to discuss the details of this project, they arrived in the Swedish winter and they just weren't dressed for the occasion. So they took them out to buy them suitable cold weather clothing, including fur hats. So when they said, what shall we call this project? They said, call it fur hat. And here's Marconi at Great Baddow, around 1960, maybe late 50s, about 1960, looking at the cars. And this building's still there, or it was last time I looked on Google Earth. It's a bit difficult to see because there's trees all around it now, but it's now used by BAE Systems. Okay, and this is a little sort of cartoon diagram of what the fur hat system, or the what the fur hat system did. And you can see that basically what it's doing is it's seeing nuclear bombers coming overhead, and it's got all sorts of different ways, countermeasures against this, like anti-aircraft guns, interceptor fighters, extremely large to scale missiles. And if you look at these two bits here, and you see the two with the big brains sticking out the top, this is, remember, this is from the time when computers were often known as electronic brains. And these are, I'm pretty sure that these are where the Marconi TACs were. Okay, I'm afraid you're not going to get many clues unless you're fluent in Swedish from reading the text on this diagram, because it is all in Swedish. So they would need a computer for fur hat. And this would have to be a state-of-the-art real-time computer developed on a very short time frame. So the perfect guy for this job was Digby. And he was assigned a bright young mathematician, fresh from Oxford University, to assist him. She was Miss M.J. Woodhead, Jill to her friends. And while they were working closely together, in 1959 to 60, romance blossomed and they became man and wife in the summer of 1960. And there they are. And the computer that Digby and Jill designed was the Marconi Transistorised automatic computer, otherwise known as TAC. And the following slide shows the TAC on display at TNMoC. Sorry, it's not a very good picture, but it's quite difficult because we've got a lot of stuff packed in that room. It's quite difficult to get a photograph without other things intruding. It does actually look better in that room now because this photograph was taken a couple of years ago and we've completely refurbished that room. So when you look at it, you won't see these pale blue walls. It's all rather neat, and you won't see the suspended ceiling anymore either. It's all been opened up to the roof. So much nicer in there now. Okay, so that's the part of the talk. Oh, a bit longer than I thought. Part of the time, part of the talk that's about Digby himself. If you want to know any more about the rest of Digby's life, there will be a story about him shortly. That's by the end of May 2021 on the TNMoC Google Arts and Culture page, which there's the link for it. Let's say the end of May. They say it'll be there during May, so it may be there a bit earlier. I've had that done for a long time, but Google are actually, all to do with the pandemic, I assume. Google have been taking the time over formatting these stories. We supplied them with a few stories, including this one. They've been taking the time formatting them and getting them up on their website. So hopefully it'll be there by the end of May. Okay, so the rest of the talk now will be about the Marconi TAC itself. Because what it was designed for was an early warning system. So what it's having to do, it's having to take radar information, and from that information, it wants to track the speed and direction that these aircraft are traveling in, so that you can project where that aircraft's going to be at a certain time. Now, these projections might be for you being able to shoot the thing down. So, because obviously you've got to fire ahead of it to be able to shoot it down. Or it may be because it's heading in a direction where it's shortly going to travel outside of your airspace and into somebody else's airspace, and you want to be able to tell them when and where it's going to cross the border, so that they can then track it or shoot it or whatever. So the two things that I'm going off what I've got on the slide at the moment, but I think it's important to put this in here. The two things you notice about the TAC is that were important for this is, number one, it's a parallel machine, and a lot of other machines around the same time were serial. Now it's a parallel machine to get the speed up, to get the real-time speed. The other thing you'll notice about it is it's got quite a short word length. It's only a 20-bit machine. Now the reason for this is you don't really need it, the numbers that it's generating, to be too accurate, but you need it to get them ready quickly. So this is a compromise. I mean, a comparison of a machine that was designed at the same time is the Elliott 803. The Elliott 803 is much slower than the TAC, but it has a word length that's almost twice as big. It's a 39-bit word, and of course that means that you can do much more accurate calculations, but you can't do them anywhere near as quickly. But the thing with the TAC was that speed was the important thing. The other thing about the TAC is it has a microprogrammed architecture. Now this means you can redesign the instruction set, if you like. So you can put very complex instructions in there. And of course, the good thing about having complex instructions is in a program you don't need as many of them. And one of the things that that Digby had found out when during his early time with other machines was that he found hardware debugging much easier than software debugging. It's much more bounded. I think that's probably the word to use. You know what you're dealing with. The trouble with software is it's a bit sort of vague, or it can be a bit vague. So so that's one of the reasons why I did the microprogram architecture, but also because memory was very expensive at the time, and if it means that you don't need as many instructions to run your program because each instruction is more complex, and you don't need to use as much memory. And in fact, the Marconi TAC never had more than 4K words of memory. Okay. In fact, his original design for it only had 2K, because he thought, oh, you never need more than that. Okay, so just, I suppose I'm just going backwards a little bit here in that we're talking about Digby, but this actually came from the Swedish report on Fair Hat. I've translated it, the report's of course completely in the Swedish language, so I've translated it with Google Translate, so it looks a little bit stilted, but this is what it says. Digby Worthy was the overall developer of the TAC computer, Marconi's first transistor computer. He created the architecture behind the mathematical calculation of the computer and is considered an important personality, great talent, and pioneer within his field. Right, now, those of you, I think there's some of you that are on, well, there are some of you that are on this call that might argue with this because you know about more machines, but I know of 5 Marconi TAC systems that were built. This is full 20-bit Marconi TACs. 3 were used, I believe, in Fair Hat, and of course 2 were used to monitor the new nuclear power station at Wilf on the island of Anglesey. But there were other variants of the TAC that were developed from it. And I believe most of these were cost reduced, and most of them were used for military purposes. There's actually documentation on a 12-bit one called Mentor, which was designed, but I don't know whether it was built. But there was certainly one called Panic, which was used for, I believe, for passive detection. Passive detection, for those of you that have never heard of it. Basically, when you're looking for things with radar, you ping out a signal and you look for quite a low amplitude signal coming back that's been echoed off the primary radar, that's been echoed off the aircraft you're looking for. So because this is only a very low level signal that's bounced back, it's quite easy to jam by just sending out a much more powerful signal to swamp it. And one of the things that was done in the early days of radar was to send over jamming aircraft that just sent lots and lots of, that sent powerful signals out. Usually sweeping across the band that could be used for radar. So you'd sweep from one end to the other of the band and then back again. And these panic computers were used to be able to work out the position of where these jamming aircraft were. They did it completely passively. They were just listening for the jamming signal. And you'd actually have 2 or 3 listening, at least 2 listening stations, which were maybe 100 miles apart, and you connect them together, and you'd have a computer that would synchronize the signals coming from both of them and work out, be able to work out where the jamming aircraft was, and you could get a track for it and be able to intercept it. So that's what the panic machines were used for. Okay, right. Now this is the nuclear power station at Wilton in its prime. It's well on its way through decommissioning at the moment. It's not been used. It's not been in use since, I'm trying to remember now when it was. 2000 and no, maybe that, no, a bit later than that. 2012 or 13, I think, when it was. It stopped generating. They were for a long time. They were only generating on one reactor because the other reactor was had some problems, but also because they were running out of fuel, the right kind of fuel. So they took the fuel rods that weren't used up from one reactor and the fuel rods, from both reactors, and put them in the one reactor to be able to get that running for a bit longer. Okay, so the TACs that were used at Wilford, they had 2 of them. They were in what's known as a high availability pair configuration, where you've got one running actively at any one time, and the other machine sitting there running, but is offline, but can be switched online and ready to take over at any time in the case of failure. So you basically, what you're doing, you've got all your peripherals, which includes all the sensors all through the nuclear power station. You've got your all the other peripherals like tape readers and tape punches and teleprinters and things like that connected to it. And you also had a shared drum initially connected to that, and you could switch all those things that are on the highways between one machine and the other in case of a failure. And here's a photograph. Basically, what we've got here is you've got a photograph 2 photographs taken from opposite ends of the same room. And if you look, you can see my cursor here. If you look here, that there and that there, they're the consoles of the 2 TAC computers. And this here is the changeover switch that changes the highway over between one computer and the other. Now, if you look on this one, this is one TAC, or all the cubicles with all the meat of the TAC in it at one end, and you can just see two of the cubicles at the other end of the other TAC. Then these other desks here, these have got Freedom Flexowriter teleprinters on them, ticket printers, all sorts of other bits and pieces that are used to monitor the alarms and things. Right, I think that's from sometime in the mid-70s. That photograph was taken. I think it's about 1976. So the two machines, they were installed in 1966, and they went operational really in early 1968. But from late 1968 until 2004, between the two of them, they ran continuously. So that for all that time, either one or both of the machines were running. I suppose it helps not having screens. You can't have a blue screen of death if you haven't got screens. Well, this is the gentleman doing the final switch off in 2004. And the TAC that we have at TNMoC is computer 1 from Wilbur. Computer 2 still exists, and it's in the Jim Austin private computer collection near York. Jim Austin is a professor at the University of York, and he has what used to be a pig farm, and what used to be the pig sheds are now contain his computer collection. He has a very large computer collection, which I believe he's actually looking for a home for at the moment. The desk containing the changeover switch he's got. We got all the spares for the TACs, so he hasn't got any spares at all, but he has got the changeover switch, and we keep sort of prodding him, saying, we'll give you some spares if you give us a changeover switch. We'll have to carry on. And there's the changeover switch, changeover desk. I believe it does automatic changeover. There's a sort of, those of you who know what I'm talking about, it has a sort of watchdog system. So you have to keep resetting the watchdog timer, and if you forget for some reason, usually because the computer's died, you forget to reset it, it will automatically switch over to the other computer. The TAC uses two types of germanium transistors. Actually, it does have a very few silicon transistors in it, but you'll see from a slide later on why they don't use many silicon transistors, and it's scarily expensive. But it mainly uses two types of germanium transistors, and it uses over 1,500 standard alloy junction transistors like the OC42. These are used where speed isn't important, like in power supplies and input-output, places like that. But it also uses almost 3,000 microalloy transistors, like the DAT1A. And the following fill code shows this. And these are used where speed is critical, like in the high-speed logic, things like that. And this is actually the transistors in the TAC, the high-speed transistors in the TAC look just like this. You can't tell because it's a black and white picture, but they're quite pretty because they're gold-plated. They were fast at the time. I mean, compared to modern, even general-purpose silicon transistors, they're grindingly slow, but they were fast at the time. They meant that the computer could run on a 1 megahertz clock, which it does. And This is comparison chart for the cost of transistors in 1964. Now, it's always really difficult to work out what 7 shillings means in modern money. I mean, you know it's 35p, but what does it mean in terms of what could you buy for it back in the day? So I've done this before, and it's the number of pints of beer, draft beer, it seems quite a good measure for these things. So the standard OC42M, which is ordinary alloy junction germanium transistor, 7 shillings, about 3.5 pints of draft beer in 1964. The microalloy transistor, about 17 pints of draft beer, or actually a decent meal for 2 with wine, 1 transistor. And the silicon transistors, there are about 40 of these in the whole TAC. £6 4 shillings each. That's about 68 pints of beer. That's, you know, that's serious amount of money at the time. When you think that modern day, a silicon PNP transistor, I mean, this is a discrete transistor. I'm not talking about a chip that has a billion in it. A single discrete silicon transistor, standard PNP transistor, about 4p, so about 1/100th of a pint. You can see these things were expensive to make. I mean, you know, as I said, the microalloy transistors, the TAC has 3,000 of these in it. So this is a lot of money. When I took over the Marconi TAC in 2013, it wasn't working. And the first thing I did was test the power supplies. And there was loads of noise on them, and the voltages were poor and whatever. And I thought, well, I'm not even going to bother looking at anything else until I've got the power supplies fixed, because you're just trying to build a castle on sand. So I started working on the power supplies. There's an example. I've opened up this power supply to give it a clean and test the electrolytics and things, and you see the muck that's inside there. The things that were wrong with them were electrolytic capacitors, and the other thing that was wrong with them was the variable resistors that set the voltages and the current limits and things like that, because the wire wound. And of course, what had happened was, over the years, the wiper on the wire wound track had stuck to the track, and as soon as you try and move it, it just rips the wire off. So I had to replace several of those as well. So not many transistors needed to be replaced. I think only 1 or 2 transistors needed to be replaced, but dozens of electrolytic capacitors. Now there's an example of a slow logic board. Now you can see the transistors with their colourful legs, and these are OC42Ds, OC42Ms rather. M just standing for a metal can that goes over the top of the glass transistor. You can see that you've got banks of diodes going into each gate. You've got 4 gates on here, 4NS5 up here, 4 gates, NAND, slow logic, 5 inputs per gate. Okay, so that's a slow logic board. This board actually is a bit unusual because it's actually a plug-in board. It plugs into an edge connector. The great majority of the TAC boards are wired straight in. The reason for this was I think they tried originally with the prototype to use all plug-in boards, but the connections weren't reliable enough. So they decided to go to fixed wiring. And this is a fast logic board. So you can see these nice gold microalloy transistors we've got here. Oh. 1, 2, 3, 4. The other thing about these, actually, you notice there's a thing called an NLM in here that isn't in the slow logic boards. This is a thing called a nonlinear module, and what it does, it's a combination of thermistor and a varistor. So it's temperature and voltage sensitive resistor. And the reason it's in there is to protect these transistors in case you get temperature goes too high, or something goes wrong with one of the power supplies and the voltage drifts up. Because these transistors, as we've already said, are very expensive. So each individual transistor is protected by one of these NLMs. The only problem with that is these are now unobtainium, and you can't get hold of these anymore. And so the only place I can get them from is by robbing them from another board. So fortunately, so far we haven't lost any of these. Right, so let's look inside the machine. So this is the first cubicle, and you can see up at the top of the cubicle you've got a few power supplies. Then you've got the memory drive circuits, and you've got 2 lots of core memory. You've got one lot there and one lot there. Each of these is 2K by 20 bits. And the drive circuits for the left-hand bank are above it, and the drive circuits for the right-hand bank are below it. So this is your memory for the machine. So this is the RAM. There's also what we would call nowadays storage, which is actually was actually originally a drum that was shared between the two computers, which was replaced later because the drums were unreliable. Was replaced later with more core memory, just a big chunk of core memory that actually emulated a drum. So it just, as far as the software was concerned, it was still talking to a drum. And down at the bottom here of this, we've also got the master clock circuit that generates the 1 megahertz clock that clocks everything all through the rest of the machine. That clock circuit, by the way, is what's called a biphase clock. So there's a master clock, and delayed half a microsecond later, there's another clock. So that you've got 2 clocks happening. In effect, then you're running on a 2 megahertz clock for certain things. But I believe every instruction has to start on a A pulse, and every instruction has to end on a B pulse. So there's a bit of a limitation there, but it basically speeds the thing up. It runs a bit faster than you might expect from 1 megahertz clock. Now we've got second cubicle. This is basically the CPU chip, right? Big CPU chip. This has got your arithmetic logic unit down at the bottom, and then you've got all the registers up at the top here. Oh, I didn't mention earlier, what you're looking at here, you're looking from the back of the racks. The front of the rack's very difficult to take photographs of because they're quite near the wall. The reason we've faced the racks to the wall is because it's much easier to get at the circuits for fault finding from the back, and so it's easier to access, and with your oscilloscope and whatever you're using to do your fault finding from the back, and then you have to go around the front to take the boards out, or if you want to replace one. We have to unsolder them from the back anyway, if the soldered inputs. So this is your CPU. We've gone from the memory chip was cubicle 1, the CPU chip is cubicle 2. This is the ROM. It's a bit more than that. You've got some micro orders which are a sort of extension of the arithmetic logic unit that we had in the previous one. So this has got the micro orders that access the microprogram, and the microprogram here, these are all diode matrix boards. So you've got lots of boards with wires coming in horizontally and wires going out vertically. In effect, you've got a cross connect, and where you've got a diode in the cross connect, you get a 1 coming out, and where there is no diode, you get a 0 coming out. So That's how the ROM is programmed. So you program it with a soldering iron and a big bag of diodes. Okay, and this is the last cubicle. We've got lots and lots of power supplies in the top of this. Then we've got the mains power control in the middle, on the control. This is actually a monitor panel, to monitor the voltage of the different power supplies, different voltage supplies. And then we've got input output down at the bottom, and that connects to these cables that go off to the these are the sort of highway connectors here that go off to the control console, control desk, and to the peripherals. So next one, there's a control desk. So we've got in these filing cabinet drawers here have peripheral controllers in them. The top one has a peripheral controller that controls access to this paper tape punch on the left here, and the bottom drawer has a controller in that controls input from the excuse me, from the paper tape reader that we have here. And then over here we have the control panel, and actually there's another one further on. I'll show you this in more detail. And then underneath this panel here is a sort of engineer's panel that allows you to access the micro program. We'll move on. There we go. So we've got the door open now, so you can access the microprogram from this panel on the left here. Oh, sorry, hit the wrong button again. Right. And here you've got the control desk. You've got basically the only excuse me, the only peripherals that we have currently on that we got from Wilfer with this computer were the paper tape reader and paper tape punch, which you've already seen, and then there's another input peripheral, which is this row of switches here, and then there's another output peripheral, which is this row of lights here, and you'll see these working later on. Okay, so that's that. And this is the order code. I don't know whether you can read that. That's about as readable as I can make it, I think. If anybody wants a copy of it, just get in touch with me, and I'll email you a copy. It's I wouldn't say it's a very complex instruction set, but it's not RISC. It's it's probably pretty standard for its time. Remember that the TACs that were at in the Fair Hat project probably had one or two much more complex instructions in them, but they wouldn't have been in the machines that went to Wilfer, because they weren't. Wilfer wasn't going to do calculation of vectors. And this is a program that I wrote myself. And the program actually is all this stuff. Everything else is comments to the right of about here. So you've got the memory address here. You'll note it only goes up to 7 because it's octal. It's an octal addressing. And the first 7 locations here are all for they're all either used as special locations. I've used them for variable storage, but they're used in larger programs. They're used for things like addresses where you put your interrupt routine so you can jump to it, that sort of thing. Or where you put your area management routine or something like that. This is a much simpler program. It doesn't need anything like that. And then the program itself starts at 0010 here, and basically what this program, this is a memory test program. So what it does is it takes whatever pattern you put on the front panel switches, it writes that to a memory location, it reads that memory location back into the accumulator register, it subtracts what should have come from that memory location from the accumulator register. And of course, if everything works, if what you wrote to memory has been read back from it, then you should get all zeros because you just subtracted what you first put in there. If it's anything other than all zeros, then it will stop with the address of the failing location in the lights on the console. So that's basically what this does. There's a whole chunk of it here. All this does round here is it slows the thing down so you can see the lights flashing. Otherwise, they flash too fast for you to be able to see. So I'll stop sharing that, and I'll just quickly show you. I'll show you the program running. Okay, so that's that was the memory test running. Right, we're back into the slideshow now. The problem that we have, I think I mentioned it earlier, is that we have only four peripherals if you include the switches on the front panel and the lights. And we can't really do anything more interesting than running that memory test. I mean, it shows you some flashing lights, but it's not particularly exciting. So what I decided to do is to set something up whereby the TAC could at least look like it was doing the job that it did at Wilfer, that is managing a nuclear power station. And what we're going to do is we're going to have a modern computer that will be simulating a nuclear reactor, as I say, without the radioactivity, so that the TAC can monitor it. And what we'll be able to do then from this simulated reactor is generate alarms. So we can say a cooling pump has failed, or we're getting burst cartridge detection, which means one of the container for one of the fuel rods has burst open and the radioactive material getting out. The TAC can then, we could put a simplified version of the program that was running at Wilfer on the TAC, and it can monitor it and do its job, which the job it actually did was to in effect to prioritize alarms, because what happens in what happens in a nuclear power station, say for example one of the cooling pumps fails, not only will you get a cooling pump fail alarm eventually, you'll probably get lots of high temperature alarms, you'll get high pressure alarms, you'll get lots of other alarms, and they'll swamp the original alarm. They could swamp it and make it almost invisible. This, in fact, was one of the problems they had at 3 Mile Island in the States. They got to a stage at 3 Mile Island because they had all the alarms coming out onto a single teleprinter. They got to the stage where the alarms were a day old. The alarms that were coming out were alarms from a day ago. So this doesn't work at all. So the idea with the TAC was that you get all the alarms coming in, and the TAC has what's known as an alarm tree, and it knows which of these alarms are likely to be a root cause when you get these other alarms with it. So it would actually put up on a screen, or several screens around the site, up to a total of 5 alarms in order of likelihood of being the problem. And of course, then the supervising engineer could say, right, Fred, you go and have a look at the first one, George, you go and have a look at the second one, and so on. And anyway, this is the way the machine was used at Wilfer, and this is what we want to try and simulate. As I said, this is all the peripherals that you've got at the moment. The other problem is that it's really difficult to connect any other peripherals because the TAC doesn't have any serial interface support. So there's nothing like a USB or an RS-232 or anything like that on it. All it has is a parallel data highway. And that's got 20 bidirectional data lines, 12 routing status register, which are address lines, and 9 coaxial control lines. These lines use completely non-standard voltages for us nowadays. So they use ground for binary 1 and -5 volts for a binary 0 for the address lines, and the data and control lines use ground for binary 1 and -10 volts for binary 0. So I designed an interface unit that converts a non-standard TAC interface into an industry standard interface, and I use TTL, standard TTL interface, that can be used to connect to modern circuitry, modern peripherals and computers. And further than that, I've actually gone further than that, so that you can connect directly via USB to an external computer. And this is the thing I've built. Is actually a bit old. There's a couple of these. This board at the end here has been rejigged now. That's an early version. What we've got is you've got these ribbon cables coming in, coming in on the back panel. You've got all the connections for the highway. So they're coming in. This one here has the address lines coming in on it, and this one here has the data and control lines coming in on it. When they've come in on these, they're then put onto the backplane. There's a backplane that goes straight across all these edge connectors that these boards are plugged into, and then we've got a card here that does the reading off the bus. So this is bus tap card. And you've got a card here that writes to the bus. So that's the bus drive card. That's the one for data, and this is the one for control. So that all these interface with the TAC. And then this board here interfaces with the outside world. You can't see it very clearly, but here, that's a little Arduino with a USB port on it. And the Arduino talks through the back panel to these others and to the TAC. So the hardware is in place at the moment, and I'm still working on getting the software to work. What I've actually found is the manual that we've got, the timing diagrams in the manual aren't necessarily 100% correct. So I'm having to play it by ear, and I've bought myself a 4-channel oscilloscope so I can monitor 4 things at once and see that they're synchronized together. So that's anybody got any questions?
Yes, there was one question specifically from Michael. Do we have more information on the interface bus?
Well, I think I've answered that with what I've just said. There's no RS-232 or USB or anything like that. All there is a parallel data highway, which is not straightforward to connect to. It isn't standard. It isn't any standard. There weren't any standards at the time. So yeah, there's a couple of other. Let me just answer these others. There's a question: aren't most computing things in the Science Museum group in storage? Yes, I'm afraid I think they are at the moment. Yeah.
I believe the Pilot ACE and the BESM, the Russian machine, are actually still on display.
Oh, are they on display? Okay.
For obvious reasons, I haven't been there for a year and a half now.
No, I haven't been there for longer than that, I'm afraid. It's probably about 4 years since I went.
Another question is, we've got the Wilva machines. We know where they are, but where are the Furhat machines?
Don't know.
Oh.
They may still be in a bunker underneath a mountain, which is where the Furhat machines went. A la NORAD, you know, similar to NORAD. in the States?
I will inquire, but I don't think they survived.
Right. Do any of the panic machines survive?
I'm sorry?
Do any of the panic machines survive?
Same reply.
Yeah. This is one of the problems you have when things go to the military. Once they go out of use, they just tend to disappear into a black hole. There's no. They probably have records of what they've done with them, but they're not available to the general public. Mentor was never built, right? Yeah.
No, Myriad overtook it.
Yeah. Good. Well, yeah, because the imp actually was a bit of a strange project because it was a complete black project, wasn't it? It was unofficial. It didn't become official until it was demonstrated working.
Well, yes, I mean, basically what happened was the circuit design guys carried on and they investigated storage and speed and things like that, and they had to build things to check whether they'd work.
Yeah.
So not unnaturally, they connected them together. And lo and behold, it did.
Yeah, good. Yeah, there's actually a complete description of Mentor amongst Digby's papers that are in the University of Manchester Library.
Yes, I think there is actually a picture of a so-called Mentor rack, but I have a feeling there was nothing in it.
Right.
It was a publicity shot for a machine, that actually never got built.
Yeah. Right.
I'm Alan, by the way, talking, and I was in Marconi at the same time, and I actually designed the tabular display system for her hat.
Oh, right.
How is parallelism implemented?
There are two meanings of parallelism. There's parallel. The way of what I'm saying with parallel is we've got circuitry that's multiplied by the number of bits in the word, so you can operate on a full word at once rather than one bit at a time that you would in a serial machine. There's a different kind of parallelism where you can operate more than one instruction at a time or more than one function at a time, and that definitely isn't available in this. That's the sort of thing you could do with a transputer machine or something like that.
Quantum computer.
Yeah, all sorts of things. Yeah. The question is about the parallelism with multiple functions at a time. No, it couldn't do that. No, it was parallel in that it operated on a complete word at once rather than one bit at a time. Which, as I mentioned earlier, a machine that was designed at almost exactly the same time, the Elliott 803, that was a serial machine, and just simply because it was cheaper to build. It was a commercial decision. But if you're building something for the military, the decisions become very different, particularly at the time when a lot of cost plus was happening. Basically, you built it, and then you charged whatever it cost you to build it plus 20% or whatever you'd agreed to be the profit margin. So you had no real reason to keep the cost down. In fact, the more expensive you made it, the more the more money you got for your 20%, whatever it was you added on.
That does appear to be the end of the list of questions. So thank you very much, Steve.
Thank you everybody for your attention. If you're interested in volunteering, go to the museum website, tnmoc.org/volunteer, and there's information there, an application form and everything. This is the sort of stuff we do behind the scenes. People who are room guides, who talk to people about the machines. There's people who, I mean, I do some of that. There's people who work behind the scenes maintaining the machines, or bringing back into working condition machines that we've been donated. I'm actually working on one of those at the moment. I'm working on a Franti Argus 500 that came from Dungeness Nuclear Power Station. I've actually got a power supply for it on my workbench at the moment, and I'm going through. So there's lots of interesting things to do. Or, I mean, even people who are not non-technical, there's jobs to do. You know, we need people to run the shop. We need people to run the ticket desk. Lots of things that are available to people who fancy doing a bit of volunteering.